Examples of the fundamental theorem of calculus part 2, which states that if f is a continuous function on a closed interval a, b, then the definite integral from a to b f of x dx is the antiderivative of f evaluated from a to b, f of b minus f of a, where f prime of x is f of x. This is known as the net change theorem. It gives us the net change in the quantity f, not the total quantity f. For example, evaluate the definite integral from -1 to 2 x cubed minus x squared minus 2x dx. If we can find the antiderivative of x cubed minus x squared minus 2x, then we can use the fundamental theorem of calculus to evaluate this integral. The antiderivative of x cubed is 1/4 x to the 4th. The antiderivative of x squared is 1/3 x cubed, and the antiderivative of 2x is x squared. F of 2 minus f of -1. We first plug in 2 into the antiderivative, and then we plug in -1 into the antiderivative, evaluate them, and then find the difference. F of 2 is minus 8/3 minus, and then f of -1 is minus 5/12. This is -9/4. But what does this number represent? Suppose we want to find the area between the x-axis and the curve f of x equals x cubed minus x squared minus 2x from x equals -1 to x equals 2. It would be wrong to set up the area as the definite integral from -1 to 2 of x cubed minus x squared minus 2x dx, because the answer it was minus 9/4. We can't possibly think that the area is negative. If we factor out this function, x cubed minus x squared minus 2x, we see that there are 3 x-intercepts, -1, 0, and 2. This is the graph of x cubed minus x squared minus 2x. There are 2 regions, one above the x-axis and one below the x-axis. The region above the x-axis will have a plus sign, and below will have the negative sign. And so the total area will be the absolute value of a1 and a2, where a1 is the integral from -1 to 0 x cubed minus x squared minus 2x dx, and a2 is the definite integral from 0 to 2 of the same function. These are the signed areas of the 2 regions. We evaluate these integrals just like we did before. The antiderivative is 1/4 x fourth minus 1/3 x cubed minus x squared. The first integral is 5/12, and the second integral is minus 8/3. And so the total area is the absolute value of the 2. 5/12 plus the absolute value of -8/3 is 37/12. And it will give us the total area, not -9/4. What -9/4 represents what the net change in the area. We see that the negative signed area is larger than the positive signed area. Therefore, the net change area will be negative as expected. What this example shows is that to find the area between the x-axis and the curve, we first need to find where the curve changes the sign from above the x-axis to below the x-axis. And we would have to subdivide the integrals into as many integrals as needed. Each of the integral will represent the region either above the x-axis entirely or below the x-axis entirely. The total area will be the absolute value of these integrals.